Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Jesse Bingham from University of British Columbia. He'll be talking to us today about some work he's done on orthogonal verification. Jesse, you want to say something else about your research? The general interests?
So for my PhD, I'm pursuing verification of sequential consistency memory model. So verifying that a hardware shared memory protocol implements a memory model. And of course, like most things in model checking, you can only model small versions. So a lot of my work is trying to find ways to check something about the small thing and generalize, so parameterized model checking. And that's what led me to the work I'll be talking about today, which isn't specific to shared memory protocols. It could be, it's general for any type, well, for a certain class of parameterized system. It doesn't necessarily have to be a parameterized cache coherence protocol. Am I start? Is the talk started?
Yeah, sure.
Okay. Okay. So in the abstract, I had indicated I talk about two different aspects of my research, but I decided that this was more interesting for this group. On Shaz's advice, I'm just going to stick to this. And yeah, so sorry, it's just going to be one development. And the title is A New Approach to Broadcast Protocol Backwards Reachability Analysis. And I should also mention that this research is in progress and the presentation is in progress. So if something's not explained clearly, please interrupt, and we'll be happy to clarify. Okay, so the parameterized model checking problem is roughly can be stated that we're given a infinite set of finite state systems. So I'll say sys of I. This I is some kind of notion of size, typically, and some property prop, and we're supposed to decide if all systems in our in this infinite set satisfy the prop. And of course, it's undecidable. But maybe if you think that you have bugs, you might take an approach like this. You start with I equals to 1 and enter an infinite loop where we check if there's a violation in the system of size I. And if we find a violation, we print the counterexample and exit. Otherwise, we bump up to the next system and try to find a problem there. So if you think there's bugs, maybe this would be a good approach to take. However, of course, that algorithm doesn't terminate if the thing is correct. So sort of the goal of this work was I wanted to find maybe classes of systems where you could take such an approach and somehow dynamically infer a convergence condition that says, okay, we've seen enough, we haven't found an error yet, we can conclude correctness. So, and I should emphasize, this is different than so-called cutoff results. The difference, I guess, is subtle. The cutoffs typically give an a priori bound on the maximum system size you need to check. This bound might be a function of the number of the local state space in a process in the parameterized system or something like that. So to use cutoffs, you use the theorem or whatever and say, okay, my system results in this number, 37, so I only need to check the system of size 1 through 37, and then we can conclude correctness as long as those 37 systems are correct. So in contrast, we're dynamically trying to decide whether we've converged in some sense. So subtle difference, but definitely a difference. So the systems we're going to verify are called broadcast protocols, and these are can be viewed as a generalization of petri nets. The specifications are a certain class of properties which say we can't reach a bad state, and the restriction on the bad states is that they have to satisfy this upward closure property. And this problem is known to be decidable. I'm just coming up with a totally different way to do it. The decision procedure uses the theory of well-structured transition systems, which is sort of a whole framework for coming up with decidability results for infinite state systems. And it turns out the broadcast protocols fall into this class. And Esperanza et al. Showed that broadcast protocols were well-structured transition systems, so we could apply this general algorithm to solve the problem. And I called this the standard approach throughout my talk.
So is it the case that, as Parsa and Shun and some of the people mentioned on the slide, they have this result that if you have a Boolean program with the stack, right, that's decidable, the reachability problem. Is that an instance of this well-structured transition system approach as well?
I don't know the answer to that question. Okay. Usually when I read papers on well-structured transition systems, they'll list a bunch of examples, and I've never seen Boolean programs in that list.
What Boolean programs are equivalent to push-down systems?
Right.
Where they're equivalent, I don't know, maybe
I speculate the answer is no, but is that...
Yeah,
your
I
answer?
should forget.
Your answer?
Yeah, there's no. Yeah,
Yeah.
I forget this. No, I cannot.
Yeah, okay.
All right.
Because those sector constitutions seem completely different flavor. And it's not model theory. I think that's a different kind
Yeah.
of
Yeah, I agree.
Now,
Yeah. Okay, so the outline of my talk, I'll discuss the actual problem we're trying to solve a little more formally. I'll try to save you the real gory details. I'll summarize the standard approach based on well-structured transition systems, talk about our approach, experiment we did, and conclude with future work and some conclusions. So what are broadcast protocols? Intuitively, a broadcast protocol represents an arbitrary number of identical finite state components that communicate in these certain ways. They can do broadcast communications and rendezvous cell synchronizations, and I'll get into the details of those in a moment. So in particular, when I talk about an instance of a broadcast protocol, what I mean is an instance where there's some fixed number of processes. But the broadcast protocol is sort of defined over an arbitrary number of processes. So to talk about broadcast protocols, we have to first talk about what their states are. And there's sort of three notions of state I'll use throughout the talk. The first is the local states at each process. We have this finite set L of local states that each process can be in. And throughout, I'll use small m to denote the cardinality of that set. And then I'll talk about a global state, a G state. It's going to be a tuple over L. So it's a finite length tuple over L that lists a bunch of local states. And finally, a vector is sort of abstracts a whole bunch of G states. And a vector is, surprisingly enough, a vector over natural numbers with m components. And the interpretation is that the ith component gives you the number of processes that are in local state I. And since the processes are identical, we only care about the number in each state. There's G states, in some sense, have more information than we need, because they actually list the details regarding which process 1 is in this state, process 2 is in this state, and the vector actually throws out the information. It sort of is a symmetry quotient type thing. We're going to introduce the notion of a weight of a vector. We sum its components. So intuitively, that's just the number of processes that it represents. And, okay, like I was saying before, these vectors abstract G states in some expected way, which I'll clarify on this example here. So these Zs haven't really come out. But so suppose you have a local state set with 3 states, X, Y, and Z. And we'll talk about an instance of the broadcast protocol, 6 processes. Process 1 is in state Y, process 2 is in Z, etc. The G state, you just list these things in order. Well, the vector is, you just count the number of processes in state X, number in state Y, number in state Z. And of course, there's other G states that have the same vector. Any permutation of these things will yield the same vector. Okay, so now let's talk about what different ways to represent states of a broadcast protocol, but the transitions are explained here. I put this slide up because I wanted to give you some intuitive feel of what types of things can be done, rather than throw up a slide of all the mathematical details of how we model this. So types of things you can do, you could have a single process locally change state without any interaction with the outside world. Rendezvous type things, typically a bounded number, like two processes get together and decide, okay, oh, you're in that state and I'm in this state, and we're both going to get together and move to new states, and everyone else stays the same. And then the most powerful type of transition is a broadcast, where every process changes states. And intuitively, some bounded number of processes that satisfy some sort of guard, they're in certain local states, can initiate a broadcast, and then when the other processes hear the broadcast, they're forced to change states based on some rule, essentially based on the type of transition and their own local state. Yeah?
Do you have what kind of systems cannot respond? Because protocol, are there protocols that I can think about that fall outside?
So, yeah, the big thing that falls out of this framework in my mind is when you want each process, every process, you want it to have the ability to remember the names of other processes. So you can't model that in this way. So if a process interacts with another process and saves the name or a pointer to that other process, and then so in the future they can get together and do something else, that won't, you can't model it in this. Right. Right.
Like it's not exactly true, even the finite states that you have in the process, they can remember some.
That's true. That's true.
Remember, so that the local states are put down to parameterized by that.
Right.
But if you want to, a process identifier is not finite, so clearly you can't do that because the local state is defined.
I think basically what it comes down to is if the number of these pointers in the entire broadcast protocol is always bounded, you can encode it in this. But if an unbounded number of processes can have pointers, you can encode it, and things become undecidable quickly because you can come up, you can encode the table of a Turing machine by pointing to someone else, and he's the next square, and he's the next square, and.
So can you encode things like chain rules and things like that, where each process communicates only to the nearest neighbors?
I don't think you can encode that in general, like for a ring of unbounded size, because. I'm sorry.
Why can't they use rendezvous to do that? Why can't they?
Because how do you remember? You have to in a ring. You have to remember who both your neighbors are, maybe one of your neighbors or something. And then so you and your neighbors say, okay, we will set a local bit to know that we're shaking hands. And then some other processes set some other local state. But no one can use the same kind of local state to remember that connection. Does that make sense? Okay, so I'll continue. So here's a bit of sort of the mathematical details, the way I've formalized it. So it's important to remember the previous slide. This slide is just sort of for your interest. We can define the transition structure of broadcast protocol as a subset of vectors crossed with the vectors. A transition is defined by binary matrix M with unit columns, and this expresses the effect of the broadcast. And we have a vector of integers C, where the weight of C is 0, and this expresses rendezvous or guards on the broadcast. The reason this requirement is here is that so in particular C can in general have negative components, and we want all the sum to 0, and that just says that processes aren't created and destroyed as a result of the transition. So given that a transition is defined by V is the current vector, we pre-multiply by M and add C, and if we can get to a non-negative vector V prime, then that transition can happen.
So by unit column, all zeros are all ones?
No, I mean all zeros except 1, 1. That basically means that everything in a certain state has to go to the next state, some next state. The next state is fully determined by the type of broadcast and your local state. So, okay, formally you can define a broadcast protocol as a finite set of these matrix vector pairs, but that's, you don't really need to remember that.
I don't understand. If you restrict M to be a binary matrix and a unit column, there's only a finite number of these.
That sounds correct.
Yeah.
But I mean, we're only allowing a finite number, so.
Okay.
So what is it catch with the unit columns? The whole column is 1 to 0.
No, the column must have exactly 1, 1, and 0 elsewhere.
So the whole matrix only has M1. At both.
Exactly, M1s. Exactly small M1s. Yeah. The column, the unit column says, the column corresponds to current state, and it says that everything in the current state has to go to a unique new state. But more than one current state can go to the same next state. You can have more than one in the row. So in particular, Petri net type or vector addition system type things are represented when the M is always the identity matrix.
So the people with broadcast rings just one in the set.
Yeah, maybe I should have just put this up to show you that there is a mathematical framework going on, but I don't really go into too much details. But basically, the semantics is that you non-deterministically grab one of these finite number of matrix vector pairs, apply it in this fashion to your current state. If it gives you something that doesn't have any negative components, then that's a valid transition, and that's the semantic. That's how the transition structure is defined. But again, this slide is more, I just wanted to give you a flavor of what can be done and how it's done. Well, I can refer you to my tech report if you want to get into more of the details. Okay, so now I'll define the broadcast protocol reachability problem. So essentially, it's a standard reachability problem. We're given this broadcast protocol, which is some kind of transition system, as we've seen, and a set of initial states of vectors init, and a set of target bad states u. And we want to know, can you call transitions to get from a state in init to a state in u? Now we have some restrictions on what init can look like and what u can look like, and respectively, init must be a parameterized set and u must be an upward closed set, and I'm going to define those things now. So a restriction on what we can say about the initial state, mathematically it's this. Essentially, we can say for each local state, so that the AIs are constants, and here we have either equals or greater or equal to, and basically we can say, okay, we have to have exactly this many processes in some state, or at least this many processes in some state. So you could express useful initial states like, say, the conjunction of these three things. We might want exactly one process to be initialized to behave as a controller type process. So that would correspond to having the initial local state of the controller equal to 1. An arbitrary number of processes initialized as clients. So we'd have like the initial client state has to be, there's really no constraint, it's at least 0. And then every other local state will say is equal to 0. So we can have everything either behaves as a controller or a client, and furthermore exactly one controller. And this is the type of thing that you might want to say and can say. So yeah, these parameterized sets aren't too important. This is how we do the initial states, but we're not going to really dwell on them too much. We will dwell on these upward closed sets, which the target bad states have to be characterized as these upward closed sets. So I'm going to define these formally, but first we will give sort of the usual partial order on vectors defined by component-wise ordering. So for vectors u and v, we will say that v is greater than u if for each component in v, it is greater than the corresponding component in u. So this is standard notion of vector dominance. Now, given a set of vectors, we'll define the upward closure of the set S just by taking everything that's greater in this partial order than the vectors in the set. And in particular, if a set is equal to its upwards closure, we say that it's upwards closed. So upward closed set has a property that can take a vector in it. Everything greater than that vector in this partial order is also in it. So when we go back to broadcast protocols and things we're trying to model, what can we say with upward closed sets? Well, we can say things like, you might want to check if a process reaches some designated error state, that's upward closed. And the upward closure here manifests in the fact that if we reach a situation where 3 processes are in an error state, we still think that's bad. Or if we have 7, that's still bad. So it's, as long as there's at least 1. And similarly, we could say something like, are 2 processes in the critical section at the same time? It doesn't matter if there's 3 processes in the critical section at the same time. It's still not a good thing. Or how about a process has read permission while another has write permission? So similar. Those are the types of things you can express using these upward closed sets.
And for that matter, the other processes, other states, that doesn't matter.
Exactly, yeah. You can never undo the badness by adding processes.
Jesse, do all the results in this talk, do they generalize to the situation where you have not just process local state, but some global state also, like some shared variable?
Yeah, you can encode that all in this framework just by having, like I said before, like one process. You basically, a process can sort of behave as various types of entities, and you initialize something to be the shared, centralized control thing that contains the shared variables that you care about.
Oh, I see. So you can make the shared state be the internal state of one particular process.
Sure, yeah. That's how you do that in this framework.
I see. So every time one process wants to write to the shared state, there will be some kind of rendezvous between that process and
yeah, exactly.
Oh, okay.
Yeah.
I am really confused by that because I thought that the local states all processes have identical.
They are.
They speak a joint union of the local state and the
Yeah.
global state. And
Someone would use it and someone might not use it.
Yeah. For algorithms, you might want to actually distinguish to save states, right? But mathematically, you can do it. Okay, so here's just a, okay, that was supposed to, this was supposed to come in afterwards, but it's just to give you an example of what an upward closed set looked like. So here, the dimension m is 2 because the screen is dimension 2. We take this grid here is the, represents each square as a 2 vector over the naturals. So this green, these things were green before the purple was on top. These represent the set that we're going to take. These represent the set that we're going to take the upward closure of, and then the purple is what happens when you do the upward closure. So I think everyone understands that. Okay, so now that we've familiarized ourselves with the problem, I'll talk about the standard approach to deciding this problem. Okay, so as I mentioned before, this approach is based on the fact that broadcast protocols are satisfied this well-structuredness property. And this is how well-structured, this is what we mean when we say a system is well-structured. We have this property here, which I'll show and I'll illustrate on the next slide, so you don't have to worry about parsing this right here. What's important is that if this holds, it implies that this holds, which is very important for the algorithms. This says if you have an upward closed set and you take the pre-image in the transition relation, you get back another upward closed set. So pre-image is of course everything that can reach the original set in one step through the transition. So this property implies this property. This thing here is explained here. It basically says that the vector order we've defined acts as a simulation relation. And so by that I mean that anytime we have three vectors that satisfy these relations, we have u prime greater than u in the order, and we can take a transition, get from u to v. So for all possible triples that look like this, there will exist a v primes with the properties that we can take a transition to get from u prime to v primes, and also v prime is greater than v in the order. So this is what it means when you have a well-structured transition system. But what we care about is more so is that what this implies is that preimages of upward closed sets are upward closed. Okay, so one more slide before I present the algorithm of the standard approach. And this is a key lemma that the standard approach uses. And I'm being a little sloppy here, but basically it says anytime you have an upward closed set, you can always represent it using this finite basis. So there always exists some set called the basis of u that is finite, and furthermore, the upward closure of that thing is u. So that's great because it says we can represent this infinite upward closed set using this finite number of vectors in this basis. So to illustrate that, okay, here's this upward closed set u. You can think of up as this way. The weights of things are increasing up the page, and there always exists this finite number of things that sort of are the lower bounds on the various sort of aspects of this set. So here's the standard algorithm, and it's essentially standard backward reachability analysis, only it's using upward closed sets and finite representations of upward closed sets. So previous reach and reach, these things store finite sets of vectors. Well, we haven't converged. We check if we've reached the initial states, and if we have, then we have a counterexample. Otherwise, we assign reach to previous reach, and then reach, we take sort of a pre-image of what it used to be. We take the upward closure of the old reach, do the pre-image, go back down to a finite basis, union in the old basis of u. And we're guaranteed to converge. And
U is a set of bad states.
That's right.
Okay.
Yeah. The invariance here is that after the ith iteration, reach will store a finite basis for the set of vectors from which u can be reached in a most I transition. So this is backwards reachability analysis.
So, the reason why you're going backwards is because the initial states are otherwise.
That's right.
Always, right?
That's right.
And so I had a question also about something that you said a couple of slides earlier, where you mentioned something about.
Do you want me to go back?
Yeah, two slides before. The one even before. I'm sorry, even the one before. Yeah, before. I'm sorry, maybe next one. Yeah.
The back report.
Transition one with the forward. Yeah, this one.
Okay.
So this one, does it need to hold for the backward transition or the forward transition?
Forward transition.
Yes, that's right.
So let me fill this in. So why does this imply? You're worried about why this implies?
Yeah, because you're doing
pre-images.
backward computation. And
Yeah.
what this gives me is the fact that I can actually take the basis, which is the bottommost points.
Yeah.
And if I compute images using that computation is very hard. That's what this gives me, right? Because I can actually use the bottom points and just compute posts using those.
Right.
And that would be a well-defined. But in fact, compute images for the entire set and not just the most part. So when you seem to be going backward, right? It seems to be the similar tradition, but actually going backward as well.
So I'm a little unclear. You're asking whether how this implies that pre-images of upward closed sets are upward closed?
Well-defined. Using,
Oh.
using the basis and representation.
So Sriram's question, I suppose, is the following: that this definition, this requirement talks about forward transition.
Yeah.
It expresses the requirement of forward transition. Whereas you're using this assumption to claim something about pre-OS. Why is there this dichotomy that something about forward transition is used to claim that you are pre-OS?
I'm wondering if there is an assumption you're saying.
Okay, so-
let's appear on the forward.
No, well, just let me explain and hopefully it'll clarify. Suppose let's take a very simple upward closed set. We'll just has one element in its basis, V. Okay, so it's this huge thing, and the preimage. We need to prove that the preimage of that thing is upward closed. So U is in the preimage, and we also know that anything above U, there will exist something above V that you can take a transition to get to. And since I was talking about an upward closed set here, that's in the thing we're trying to get to as well. Of course, everything I said generalizes to more things in the base. Good. Okay. So I'm not done talking about this.
By the way, let me comment that I think for the error states, it's actually a reasonable assumption to say that it's upward closed. But I don't think it would be reasonable to assume that the initial set of states would be upward closed. It would seem very counterintuitive, right?
Yes.
Most of the initial sets that you would want to say, they would not be upward closed.
Right. Yeah.
Right? Okay.
Yeah. That's why they're not in the. Right. Yeah. Because you want, say, one thing to be the controller.
Yeah.
You don't want a whole bunch of controllers.
Exactly.
Okay. So one thing I should point out is that we'll see a few instances throughout here where I have the upward closure thing. And of course, the algorithm's not really computing the upward closure because that's an infinite set. But you also have to take my word for it that everywhere where you would want to, where it's implied that we're doing that, we can really decide whatever we're trying to figure out. For example, this containment here can be done just by looking at the finite bases, similarly with the intersection with initial states. And in particular, the fact that this is sort of decidable doesn't follow from this simulation condition. But for broadcast protocols, this can be done. Given finite basis for reach, we can compute a basis for the preimage. Okay, so that's the standard algorithm. Just again, it's standard backwards reachability analysis done in one fell swoop, and it's guaranteed to converge with some other theorems, and that's how it works. Yeah. Yeah, the ordering has to be this well quasi-ordering. And the ordering I've given for the vector dominance is one of those things. It's just particular well quasi-ordering. So, yeah, there's this whole theory that I brushed under the rug that I had nothing to do with developing. Yeah, and this has to be, the fact that this is decidable doesn't fall out of the definitions either. But for broadcast protocols, it works. So, okay, so I've got a little cartoon that shows the iterations of that algorithm. So we start with the upward closed set U, but we don't really start with the upward closed set U. We start with the basis for U, the light blue. We do preimage, but we don't really do the preimage. We get this light pink basis for the preimage. But we know that the union of those two sets of bases will give us some finite basis for the things that can reach pre in one step. We take another preimage, but we really are just figuring out a basis, and the union of the light blue, light pink, and yellow gives us a finite basis for the things that can reach U in at most 2 steps. And we iterate, and there's a theorem that says we'll reach a fixed point, which will give us a finite basis for the transitive preimage of U.
So, just to understand, just to test my understanding, to prove that a fixed point will be reached requires some theories that have not been mentioned, that you have not mentioned there.
That's right.
You say that the unions of these different colors give you a finite basis, but just taking the union of those points does not give you the smallest basis.
No, that's true. Yeah. I don't care because this isn't my algorithm. But the next slide should address your question. I haven't really said. I've just said if you collect them all, that's good enough. But of course, there's a huge amount of redundancies, and in a real algorithm, you want to do something about that. So, yeah, that's a good point. So, yeah, this is related. If you actually were to implement the standard algorithm, the number of vectors you've got here is going to blow up. And we haven't said anything about how they're being stored and issues like removing these redundancies that would clearly exist. So these are things addressed by Delzano et al. In a few papers. And they propose using these things called covering and sharing trees to represent sets of these vectors. And so you, rather than just use these finite collections, you're using this sophisticated data structure to store these sets. So they're analogous to BDDs for bit vectors, except everything's more complex. So just to reiterate, the height of these, and they're similar to BDDs too. They share common prefixes and stuff like that. And, the height of them is, of course, going to be m, because that's the width of the vectors, the number of local states. And unfortunately, unlike BDDs, when you're checking for convergence in the backwards reachability with using CSTs, it's co-NP hard to determine convergence in the size of the CSTs. So that's a serious drawback, and Delzano et al. Come up with some sophisticated heuristics to try to deal with that. But you're stuck with an intractable problem.
What have Delzano et al. Verified using all this stuff?
They've verified a lot of petri nets, small petri nets. Well, I shouldn't say small. I don't know enough about petri nets to say whether something's small or not. But, maybe a petri net with 30 places. Okay, so now we can get on to how we're tackling this problem. So here's a high-level view of our algorithm, and it looks remarkably similar to, I think, my second or third slide, where I had this thing that didn't terminate if it was correct. But we're going to claim that we can add, rather than have a 1 here, we're going to have this condition called converged that is going to allow us to terminate at some point. So I haven't told you what that is yet. We're going to compute, okay, so this is just some notation I haven't defined yet, but when I take a set and put braces around it in subscript, that just says take everything in that set that has weight I. So take everything in the upward closed set that involves I processes. In particular, that's a finite set. So we can compute the transitive preimage using finite state model checking techniques. And throughout, I'll talk about R of I as the transitive preimage from U in the broadcast protocol I processes. Yeah. Yeah.
That is a finite state model.
Yeah, that's what.
Worry about upward flow sets and all those other things that we talked about finite state model. So for me to solve this finite state model problem,
Yeah.
why worry about upward flow sets?
Why am I worried? Why are you worried?
Because why should I think about upward flow sets and other
Oh.
things which are necessary when you range these spaces?
All the upward closed set stuff was the theory behind the standard approach.
This has been mentioning that at all, true. U is simply the vectors in your state space.
They do not have to be upward flow.
Well, yeah, they do.
U doesn't have to be
For
upward flow.
convergence problem, right?
Yeah.
So that was exactly the confusion.
Oh, okay.
The confusion was that precisely when you said, I was just thinking that each iteration of the algorithm deals with finite spaces.
That's right. Yeah.
Then the pre-star is completed over a finite space system.
Yes, but this convergence condition is going to depend on the fact that that's upwards closed.
So I'm
There's something
confused.
I'm missing.
I'm confused.
Yeah, calculate it.
Oh, okay.
So
Okay.
when you say the vectors in U, what is
U
U?
is the upward closed set of bad states.
What is the upward flow set of bad states?
So presumably we have some finite basis that represents it, and we can say, okay, it's computable then to give me everything above that that has I processes.
In sum?
I'm sorry?
Is it sum in I problem? The sum of, so each vector is a vector of natural numbers.
Right.
And you want the sum when you say exactly I problem?
Yeah, the sum is I. I call it the weight of the vector is I. So that's what we're asking for here, and we compute transitive preimage. Throughout I'll use R of I to denote this set. So of course nested in here is another loop, right? We're doing backwards reachability analysis, but we can express it in one line because these are well-known techniques.
So I guess the answer to Sriram's question is, you have not talked about converged yet.
No.
How exactly converged will be defined.
That's right.
And the correct definition of converged depends on U being upward closed.
That's correct.
Okay.
One question about the number of processes. So can the transition not change?
The way the broadcast protocol is defined, it can't.
If you're assuming
I'm assuming that. Petri nets, of course, in general, you can have transitions that create or destroy, but you can always encode. You can encode like a Petri net coverability problem as an instance where all transitions have the same incoming and outgoing weight. So it's okay when I say that this is a generalization of Petri nets. I haven't thought a lot about what happens if you decide, okay, let's allow things to change weights. It was easier for me to think about it when that didn't happen, but anyway. Okay, so yeah, haven't defined converged yet, haven't defined this intersection check, but this is essentially what, at a high level, what the algorithm looks like. Okay, so this is the convergence theorem, and this suggests how we can check for convergence. And don't worry if it doesn't make sense, because the next slide, I think I give a good illustration of what it says. But the one thing, well, there's a few things I haven't defined yet. Don't worry about that. But delta here is, of course, tells us how many containment checks we have to do here. And I haven't told you what delta is. Delta is the maximum number of processes guarding a transition. So, for example, if you have, for a Petri net, it's the maximum in degree of any transition. So essentially what it's saying, if we have these delta containments for some n, we can conclude that the entire transitive preimage of the upward closed set U can be expressed as just the upward closure of the backward reachability sets of the broadcast protocol of size 1 through n. Okay, so this will hopefully shed some light on what that was saying, and also sort of emphasizes what the approach that I'm taking looks like. We start with this upward closed set U. These horizontal stripes correspond to the system of the size 1, 2, 3, 4, etc. So in particular, like in here, this is U with the braces subscript with 4. Okay, so we compute the backwards reachability of R1. And notice these dotted lines denote the upward closure of that set. And then we'll do the same thing for 2. And in this case, what's interesting is we've gone sort of outside of what the upward closure of R1 looked like. So in a sense, these are the new things we've learned about the system of size 2. Everything that's in R2 that was in between the upward closure limits of R1 was sort of we already knew about that stuff in some sense. Okay, now let's do R3. Well, in this example, R3 turns out is contained in the upward closure of R2. So when I first started doing this work, I was convinced, well, that must be the convergence condition. So I spent a long time trying to prove that was the convergence condition and wasted a week of my life because it's not true. You can then you can go to a case where you go outside of the, and find new things. So anyways, so we keep doing this until we reach some n, and now I've got the upward closure of n. Oh, that U is not supposed to be there. In this green field is the upward closure of R of n, and we find that the next delta sets are all contained in R of n, the upper closure of R of n, and that is sufficient. Our theorem says that is, we can conclude that for any I up here that we'll never be able to go outside of these bounds again. So we're sorry, delta's, again, so I haven't formally defined it. It's intuitively, it's the maximum number of processes that can guard a transition.
the reason you're saying it's efficient is because there can't be any sort of unaccounted for transition, which would allow for the maximum number of possible processes to cooperate to give you some median.
That's intuitively what's behind the theorem. Yeah.
Just to test my understanding, the 1 week that you wasted, you were trying to prove that delta is equal to 1. That's correct. But it turns out that you were trying to prove it for delta equals 1. It turns out that you don't need, you have to actually bound it by the number of processes that can participate in it.
It was less than a week.
Okay. All right. Okay.
Because, you know, I'm new to this type of research, and I'm familiar with, you know, standard backwards reachability analysis in a finite domain. And of course, there are different things, but in there you converge one iteration, you converge and you're done. So I thought, well, you know, hopefully the same thing happens here. But I think that was a naive assumption, but I learned a lot. Okay, so we've got, this is all great, but are we guaranteed to find such an end? If not, then we don't even know if our algorithm is going to terminate. It turns out that there does exist some end, and all this well-structured transition system theory, it follows quite trivially from that, basically because the transitive preimage of the upward closed set is upward closed, therefore it must have a finite basis. The finite basis must have a maximum weight vector, and so we're guaranteed to get this convergence before we get there.
This n cannot be computed by some kind of syntactic analysis.
That's something I think not, but I haven't really thought about it too much. Yeah.
So essentially, this is a different algorithm for the same problem.
Yes.
But each iteration of the algorithm only uses a finite technology.
That's right.
Is that how it is?
That's exactly how you should understand it. And the main contribution was figuring out how to detect convergence. Not as interesting as so the other thing is we still have to figure out if we've intersected the initial states, and I have a theorem that covers that, so I'm not presenting it here. But we can, for each one, we can do each backward reachability set, we can do certain checks and conclude if this holds. I'll point out it's a little more involved than just checking if these things intersect in it, but anyways, it's all taken care of. It's cheaper? Well, the co-NP hard problem was checking for convergence.
Right. But
Yeah.
it's not checked at every step.
Are you talking about checking for intersection with the initial states? Well, you don't have to check at every step, right? You can wait till you can check at various points.
Yes.
Yeah, you could wait till you converge at each level, or you could wait until you converge at the very end of the algorithm, presumably.
If you take a class of problems for which like three columns work and you try to do a static bound, and normally you see that because you're covering everywhere, okay?
I haven't done that. I would venture a guess the answer is yes, because this is sort of very, his bounds, you know, you a priori there's some function, and it just says, the theory says that in the worst case you have to check this many. So then you go ahead and do that, but maybe all the interesting things were done after you had 3 processes and you went to 48 for no reason. So this is sort of the tightest cutoff, maybe one way to look at it. Okay, so how should we represent the R of I's in our approach? So let's use BDDs, because everyone knows they've been known to distinctly represent large state spaces, and they're, in some cases, and their algorithms, there's efficient algorithms for their operations. Now, we're going to compute RIs as subsets of I tuples over L. So we're going to, our representations of the RIs are going to be actual sets of G states. And we can encode such things using, of course, I log base 2 cardinality of the state space of L, Boolean variables.
So if you do that, don't you lose all the symmetry?
You do, yeah. So this is something I need to look at. You lose all the symmetry. Yeah, the vector representation sort of gives
Give the
symmetry reduction for free. Whereas here, I've completely lost that. So that's the first thing that I noticed. If I want to criticize my own work, that's the, yeah. Okay, so we can employ symbolic model checking techniques because we have these BDD representations. I'll use R sub BDD if I when I want to talk about this actual BDD that represents that set. So, yeah, okay, here's an example. If the local state space is L sub 1 through L sub 3, the upper closed set says, give me everything that has at least one process in L sub 3. Suppose when we look at the system with two processes, R2 contains these vectors, then our BDD will store this. This is exactly what Chaz's point was saying. We lose this, like the green here blows up into two things, the blue blows up into two. So this shows you the correspondence between the two representations. Okay, great, but how do we, we've got this nice convergence theorem, we've got this BDD representation. How do we do the necessary checks? We need to do checks that look like this in our convergence theorem. And in particular, if you think about our BDD that represents this thing has more variables than the BDD that represents that thing. So it's like comparing apples to oranges when you're looking at the BDDs. So how do we decide this when we have BDDs representing these things? And we've defined this operation called existential lifting that, in a sense, takes this and lifts it up sort of to this guy's level so that the comparison, you can do a comparison. So here's the definition of existential lifting. So we're given this set S that's I tuples over L, and S, the existential lifting of S is a set of I plus 1 tuples over L, defined like this. For every I plus 1 tuple in the existential lifting, or the tuple is in the the tuple is in the existential lifting precisely when we can choose a K, a component in the tuple, such that if we delete that component, we get something in S. And intuitively, X is in the existential lifting. If we can delete a component, we get something that is in S. So here's an example. In our algorithm, we end up with BDDs here, R sub BDD of I. The existential lifting is going to be precisely that set. And then, well, I haven't shown it, but then the next step in the algorithm, you compute the backwards reachability of I plus 1, and then it would maybe be bigger or not than this set. But now we have things that we can actually compare. That's how that's handled. So here's the theorem that says this containment holds. This is the check. We need to do these types of checks in our convergence theorem, and it turns out this is logically equivalent to this check against BDDs. So here's application of the existential lifting operator, and this is just normal logical implication between BDDs. And in fact, whenever we need to check this, it will always be a bidirectional, so you can do this in constant time. Okay, now I'll talk about the experiments that I did. The motivation behind the experiments, and I make no qualms about it. I tried to come up with an experiment that would show a situation where my approach is superior. And here's the rationale behind it. And clearly I need to do more thorough analysis, but this was very rudimentary. These CSTs of the standard approach processing, they're kind of like BDDs, and they have a constant height, which is the number of local states. If the number of local states is really big, then these CSTs have the potential to get really, really fat in the middle and blow up. Now, what about our approach? We encode the state of a single process using a logarithmic number of BDD variables. The largest instance of the broadcast protocol we have to analyze has this n plus delta processes. So our BDDs have at most this many Boolean variables. So again, I mean, we've got BDDs here, CSTs here, but we're just taking as a very coarse measure of how big they can get their height. And this is what we come up with. This is the height of our things. This is the height of the standard approach. If if this is much bigger, then we might think that, okay, we're going to do a lot better. So in particular, you expect this to hold if the local state space is large. And these things aren't too bad. So to test this hypothesis, I came up with a family of petri nets that are these are parameterized petri nets. So this parameter isn't the parameter in the normal sense of the parameterized model checking parameter. This is actually controls the number of local states in the petri net. So H is a knob that lets us adjust how many local states there are. The local states space is 3 more than H. Delta is 2. So in particular, everything that happens are pairwise synchronizations. There's pairwise rendezvous. So delta is 2. And it turns out convergence happens for n equals 4. So that means when you plug the numbers in, the CSTs have height 253, whereas our BDDs only have height, at most 48. So here's the gory details of this system. It's the ME stands for mutual exclusion. Basically what I did was I said, let's do a simple mutual exclusion implementation. And I want to find some way to add a whole bunch of states. So I'll say, whereas most mutual exclusion type petri nets have one place representing the critical section, I expanded that into this long chain of places. And the length of this chain is controlled by the parameter H. So these two places are thought of as the control process. It's either in state not in or in. In means it's allowed one of these client processes to move into this chain. And once it's here, it won't allow anything else. And then a client process can move on this chain and then either make its way to the end or non-deterministically go back to this non-critical section. And yeah, the way it works is that the controller ensures that at most one client is in this chain at any time. The property we were verifying was that you could never reach a state with 2 processes in this end state here. So here's the results. This top line is the CST software that I got from colleagues of Belzano. They warned me that they didn't feel that it was efficient. It was maybe 3 or 4 times slower than it could have been if they spent some time optimizing it. You could probably arguably make the same claim about my software. Here's this is my implementation, and there was this lengthy translation process that really could be eliminated. And so this curve gives you sort of what would happen if you remove that translation. Basically, I had to, when I hacked this all together, I had some Perl scripts that would take my broadcast protocol representation and translate that into SMB, and then the SMB was parsed, and you could probably remove this SMB step from a real implementation. So that specifies that. And I should mention that the model checking done here was all written by me. So this is very naive model checking 101 BDDs here. There's no sophisticated partition transition relations or anything involved in the model checking that is happening in my approach. Okay.
You did not use SMB as a black box. You actually wrote some code inside SMB.
I didn't even use SMB at all. I used some software I got that would parse a BDD SMB file and give me a bunch of BDDs. Then I wrote all the code that
And then you wrote the
yeah.
point.
Yeah.
Okay.
And the stuff to do the existential lifting.
One thing I mentioned before, is NEH equal delta equal H?
No.
Right?
No.
So then why do we see, so does N become H then?
No. The only thing that depends on H.
Why is it getting slower?
L depends on H.
It's H it gives me a knob to control the size of the local state space.
Right. So you still have to explore more and more how or do you increase the number of states, not the number of processes?
Right.
Yes.
Yeah. That H was a different parameter than.
So I sort of expected that it wouldn't actually get more
But you still.
have to
step in which iteration is now long and in fact the backwards version is now long and
It's more complex, and once you get big enough, you have to add another variable to encode the future work conclusions. I clearly need to do more experimental evaluation. Complexity analysis, like all these, I've thrown around all these BDD operations, but I'd like to, quantify exactly what can happen there. Optimizations. Actually, the algorithm I've used in the experiments has an optimization I didn't mention here, and I think there's more that could probably be applied. And I'd like to apply to other classes of systems, so other discrete, well-structured transition systems are amenable to this approach. And like we talked about, I think early on in the talk, situations where we have a bounded number of process pointers. And in particular, there's this caching protocol proposed by Steve Gurman that everyone likes to verify, and I think I can use this approach to verify that. So that's one of my next goals. Conclusions: we've got a new approach to parameterized verification of broadcast protocols that uses BDDs and classical symbolic model checking. And intuitively, we might expect it to outperform the standard approach when we have a large number of local states and it converges for a not too big n. And my hunch is that many systems of practical importance might have such characteristics. That concludes my talk. Any more questions? All right, let's come to speak with it. Thanks.
And I think all the illustrations you did, you probably spent a lot of time on that.
I did, yeah.
Yeah. I did. So we have about 20 minutes before your appointment with Tom, so we can talk some more if you want.
Sure.
Yeah?
Sure.
Okay, let's
Do I
take
need to do
your...
anything, or?